So it is a honor for myself to announce you the second conference of this session. It's going to be presented by the Professor Xavier Gómez-Mont with the title, oh my goodness, I just lost it, I'm sorry. Here is it. On the non-periodic part of the monodromy of the plane curves singularities. So Professor Gómez-Mont, please.
I would like to thank the organizers for inviting me to give this talk. And so I'll say this in Spanish. Enrique fue mi maestro en unos seminarios que dirigió en el Departamento de Matemáticas del CIMAT en los años de 1973 a 1975, cuando era yo estudiante de licenciatura en la UNAM e iba yo a Zacatenco a participar en los seminarios. Durante esos años se leyó los libros de Göning sobre superficies de Riemann, con quien posteriormente realicé una tesis doctoral en la Universidad de Princeton, y el libro de Wells, que me introdujo a la teoría de Hodge, temas de los que hablaré hoy. Así que ahí se ve constancia de que la semilla que sembró Enrique en mi cabeza junto con los otros alumnos que tenía allá del Politécnico y del CIMAT. Muchas gracias, Enrique, y muchas felicidades por tu cumpleaños. So I'd like to begin with a recent thing I received from Thurston that says that mathematics is not about numbers, equations, computations, or algorithms. Mathematics is about understanding. En fin, entonces, so the algebraic object that we are going to analyze is a polynomial in two variables, in two complex variables, or more generally a convergent power series in C2. So if it's a polynomial, the information that you need to set up the thing are this finite number of complex numbers. This constructs the polynomial, and this is the algebraic object. Now, we're going to associate to this simple algebraic object a geometric object. So we fix a small ball around 0, and we obtain a partition of the ball by the fibers of the by the fibers of the function. So these are f lambda is the set of points where f of p is equal to lambda. So this open set will be decomposed into the disjoint union of surfaces of two-dimensional real manifold, except at the origin, because we are assuming that we have a singular point. And if we restrict the values to a small disk and take the inverse image, that's this set U, we obtain the following situation. So, usually one analyzes f equal to 0, one of the fibers. So in this case, we're assuming that 0 is a critical point of the function f, then we may factor f into its irreducible factors in the ring of germs of holomorphic functions. And so this fiber over 0, f0, is the union at 0 of S0 disks. So it is a connected singular surface with S0 boundary components and one singular point. So we will be obtaining from the analytic geometry of the F, we see that here we have S0 boundary components. Now each disk, which is parameterizing the irreducible components of F0, is embedded in a noted way in C2 according to its Puiseux exponents. And they are mutually noted, measured by the intersection multiplicity of the different factors. So the fiber over zero is extremely simple because it consists only of a finite number S0 disks embedded in a complicated way. And if we intersect with the sphere, then these circles, which are the intersection with the sphere, will be curves which are noted. Now, we will consider not the value 0, but a small value lambda. And then in this case, the fiber of the function is a connected oriented surface with compact boundary, F lambda bar, and it has S0 boundary components, where S0 was this number of irreducible factors of the function F. G is the genus of this Riemann surface with boundary, and what will play an important role in what follows is this first homology group. So the first homology group of this Riemann surface is 2G, which corresponds to the genus inside, plus these boundary components that contribute to S0 minus 1 independent elements in this in this first homology group. Now, this number, which is topologically defined, may also be obtained as the codimension in the ring of germs of holomorphic functions of the ideal generated by the partial derivatives of F. And so here is where the mystery begins, because there is this relation between the topology and the algebra, that we can see that this number, which is computed algebraically, is giving us information about the topology, and one would like to understand different subspaces of this H1, and to see which are the corresponding subspaces in this vector space. So this is just the beginning of a relationship between topology and algebra. So in our case, that we're assuming F has an isolated singularity at 0. If we take this set, open set U minus the fiber over 0, it gets mapped into the disk minus the origin. Then this is a locally trivial fiber bundle with fiber F lambda, and the monodromy map is the map which is obtained from the fiber F lambda to F lambda, obtained by lifting a circle in the values of the function lambda. So we obtain an automorphism, which is the monodromy map, and it is unique up to isotopy, and it is the identity on the boundary. So this procedure associates to the function F this fiber F lambda with a diffeomorphism. So it associates a compact surface with boundary and a diffeomorphism up to isotopy, and which contains information of F over the punctured disk. So we can see that we are not only looking at the value at the fiber of F over 0, but the fiber of F at the regular point. Now, the correct picture that I want you to have in mind during this is the following. I'm sorry. So, I like to use I like to use the following picture. So, and to have in mind of this F lambda. F lambda is this Riemann surface is highly structured in the sense that we will find some subsurfaces that we will call to have something in mind, some neurons, and then we have these which are the axons, which are uniting the different neurons. So in this sense, we don't so the picture, I'm sorry. So the picture is the following. So we take the closure of this Riemann surface F lambda, and we will see that it is the union of subsurfaces Sj. Now, the intersection of two different subsurfaces will be these loops over here, and the monodromy map preserves these neurons, preserves the axons, and it moves them horizontally in this picture. So, the monodromy map, the geometric monodromy map, which is an automorphism of the Riemann surface, is preserving these neurons and is preserving these axons, and it is permuting the neurons and it's permuting the axons. So we have this information. Now, if we apply the theory of resolution, so how come that we obtain this description? So this description, this partition of the original Riemann surface of the fiber F lambda, it follows from the theory of resolution of plane curve singularities. And so this theory, what it does is that you take the origin and then you start blowing up, you blow up the origin, and then you make the strict transform of the fiber, and you see where the points of the fiber now intersect the exceptional divisor, and then you keep on blowing up until you get to a situation where the strict transform of the fiber intersects transversely all the exceptional divisors. And this is what's, that this process is maybe carried through is what is the content of the theory of resolution of plane curve singularities. And then we pull back the function to this blown up manifold, and what we see is the following. So here in this picture, these black things over here, these are the exceptional divisors. And then at each intersection of the exceptional divisors, then the function looks like x, y equal to a constant. So this means that in a small neighborhood, what we will have will be annuli. So in each, and it may be several annuli. It depends on the multiplicity of the different exceptional divisors, the nature of this xm times y, xm1 times ym2. So this gives us this annuli, which transform into these axons. This come from the intersection of the two exceptional divisors. And then on each exceptional divisor, if you restrict to the complement of this, you remove these squares, and then the projection map is a covering map onto the Riemann sphere minus a finite number of disks, which correspond to this. And so from the connected components of this covering surface is where we obtain the neurons. And so the neurons are obtained from the fiber near the exceptional divisors, and the axons are obtained near the intersection of two exceptional divisors. And then the monodromy map in this picture, it will be preserving these curves, this joint family of curves in F lambda, and it will be permuting the different components. So it will be permuting the different neurons. And then if you iterate to a convenient number Hn, and this number n is something which is significant for this description, then the map will be the identity on these surfaces and on these annuli, which are around these loops here. It will be a then twist of a ring of twisting order omega L. So a then twist is you got the neuron, and so now you have a tube, and then you make omega L turns, and then you glue back. And so this means that this is how the monodromy map looks like. So it is periodic on the neurons, and on the axons has this twisting. Now, the fact that there is this twisting means that the non-periodic part of the monodromy is coming from the twisting in the axons. It's the part which comes from the neurons is periodic. So now, if this resolution process we call sigma map from U tilde to U is a resolution process of the function at 0, and we let EK be the exceptional divisors and the strict transform of the original fiber F0, we construct what is called the dual graph of the resolution. So we put a point for every exceptional divisor, and we unite with an edge two exceptional divisors if they intersect. And for the irreducible components of the curve, we put these like things with arrows, and it is known that this graph is a tree. Now, I want to show you how to construct from the covering Sj, which are these neurons, and Al, which are these axons of the fiber F lambda, a finite graph gamma tilde that codifies the connectivity properties of the covering. So this graph comes with a periodic automorphism. So the graph, this gamma tilde will come with a periodic automorphism and a map from the graph, from this graph into the resolution graph, and it is H gamma invariant. So in this picture, we have the following. So here we have the graph of resolution. So it looks like all these are these exceptional divisors. Here we have the curves that it has two irreducible components, and all these are irreducible divisors. Now, for this example that I constructed this resolution graph, this graph, which I'm going to show you how to construct, looks like this. So there's this map going down, which tells you which are the components. These are the neurons sitting above this exceptional curve. These are these neurons on these exceptional curves, and these are the axons. And so from this picture, you get the connectivity properties of the covering that and then so this here, these are like contractible parts of the graph, so they don't bring any topology. These also, they don't bring any topology, and the topology here is built like this. You go like this, and then you come back through one. Then you go into one, and then you come back in the other way. And so if we look at this other picture that we have, so the non-trivial homology, it will be coming from, you come through these paths, you pass through these axons, then you pass through different neurons, and then you come back, and then you close. And so this is giving a part to the non-periodic part of the homology of this surface. So this construction of the graph, I won't spend much time here because I know it's you know, it's a little technical, but anyway, so around the exceptional divisors, so the covering is done by taking this UK is the piece of the Riemann surface which is contained in a neighborhood of the exceptional divisor K, and then you take the connected components of the Riemann surface in this tubular neighborhood of the exceptional divisor, and then you take the intersection of these two pieces. And so these are the neurons, and these are the axons. And there is this way of obtaining this description. And so from the resolution graph of the original function, we get this other graph, which is covering with a finite to one map. And so this is called the Nielsen-Thurston graph of the manifold. And it has a conclusion from this is the following. From information on F0, that is resolution of singularities, provides for us a monodromy invariant partition of F lambda by connected subsurfaces, and the intersection pattern between these subsurfaces is codified in the graph gamma tilde, on which the monodromy acts through a periodic map. So this gamma tilde is going to contain the non-periodic behavior of the monodromy map. And in some sense, is there a question? And in some sense, it's surprising that it's a periodic map. Now, so this gamma tilde, what it does, it contracts these neurons to a point, and then it sends the axons to some edges of the graph. So in a way, this Nielsen-Thurston graph concentrates the connectivity properties of the and let me see. So now we will. So here we did this in pieces of the surface. Now we will do this homologically. So we recall that the homology, the first homology group of the surface F lambda is done by taking closed paths gamma k with weights, integer weights, and we divide by the boundary of subregions S prime with weights. And so this is the first homology group. So like if we have an axon like before, so this homology class is on homologous to this other one. And in here, if we have what's called the pair of pants, then we have that this loop over here, this gamma 3 is homologous to gamma 1 plus gamma 2. So also important in what we are going to describe is the intersection of cycles, which is, it gives us an antisymmetric bilinear form that you take one cycle and another cycle, you put them in general position so that they intersect transversely, And then at each point of intersection, you count with a +1 or a -1, depending on the orientation. And this gives you a well-defined pairing bilinear form in the first homology group. The radical of the bilinear form is the set of homology classes which are 0 with respect to everybody else. And so in this case, we see that these are given by the boundary components, the boundary components. So if we take the first homology group modulo the submodule generated by the boundary components, then we get a non-degenerate bilinear form. Now this non-degenerate bilinear form is the same we're going to call F lambda tilde. This is the surface obtained by gluing some disks on each boundary component. So inside it's a Riemann surface, but we are going to convert it into an orientable surface just by gluing these boundary disks, and the coproduct is the non-degenerate bilinear form given by this compactified surface. Now, the homological bundle is the bundle over the punctured disk formed by all the 1 homology groups of F lambda. And so for every point λ1, we put this first homology group with its coproduct. And then another one, we put this first homology group with its coproduct. And so this becomes like not a vector bundle because it's not a vector space, it's a C module, but it's similar to a vector bundle over the punctured disk. And the monodromy map, the algebraic monodromy, is the map induced by the geometric monodromy in homology. Now, this is preserving, since it's a diffeomorphism, it preserves coproduct. So it's an automorphism of the vector space with the coproduct, and it codifies the homological information of the first homology groups of F over the punctured disk. Now, as I mentioned, part of ingredient that I learned from Enrique is this Hodge theory. So from Hodge theory, they say algebraically, one may decompose this linear automorphism M lambda, the monodromy, the algebraic monodromy, into a periodic part. There they call it the semi-simple part, but since the eigenvalues are roots of unity, it's a periodic part, and then another part which is the unipotent part. And this unipotent part may be written as the identity plus n, where n is a nilpotent matrix. And then the theory, the Hodge theory, says you take the logarithm of the unipotent part of M lambda, and this you call n. And with this, in Hodge theory, they construct a symmetric bilinear form in the following way. So this is these double brackets sub lambda. So you apply n on the first factor, and then you do coproduct. So you take alpha and beta, you apply the n, this unipotent part of the monodromy to the first alpha, and then you coproduct with beta, and then you do the intersection and you sum. And it turns out that this is a symmetric bilinear form in the sense that if you apply the n to the first factor or the n to the second factor, it's the same. So one creates in this way a symmetric bilinear form. So the objective of the research that we are explaining now is to give a geometric meaning to this bilinear form. So this bilinear form is constructed using algebra and using a Hodge theory, which is some harmonic analysis. So algebraically, still, we may define a flag. So the annihilator of n, so this is the set of points where n vanishes. So this is part of the homology. And since n squared is equal to 0, the image of n is contained in the annihilator of n. So we have this flag. So we're beginning to distinguish subspaces of the first homology group. So there is one which is this annihilator of n, and then there is this image of n. And then algebraically, we obtain an isomorphism. If you take H1 divided by the annihilator, and then you send it to the image of n, so n vanishes on the kernel of n. So you have a map from n into H1, but actually it goes into the image of n. And so one sees that this is an isomorphism. And so this bilinear form that we want to understand, this symmetric bilinear form, so one could ask, is this bilinear form positive definite? So in principle, from this algebraic construction, there is no reason a priori why should this non-degenerate bilinear form. It's non-degenerate because we killed the kernel, the annihilator. So why should this be a positive definite? So this is the question we answered using this geometric description that I gave before. So now we're going to, instead of constructing this algebraically, we're going to construct this geometrically to prove that this bilinear form is positive definite. So we're going to construct a flag 2, which contains 2 sub-vector spaces in the first homology group. So the smaller one is the homology generated by these closed loops in the axons. So we take all the axons and we consider a loop around each of the axons, and we consider the module generated by these axons. Now, this is the next sub-vector space, will be the vector space which is generated by all the homology groups which are contained in the neurons. Since the neurons, homology of the neurons contain the homology of the axons, we obtain this contention. And so, we call this C1CL for some reason are these vanishing cycles, because when we make lambda go to 0, we can't make these small circles go to 0, and so we will obtain some compact Riemann surfaces with ordinary double points. When we contract these circles to a point, then these connected components will convert themselves into irreducible components of a singular curve, which is called the semi-stable model of this fiber when we contract these circles to a point. And so then these H tilde periodic are the ones which are contained in the neurons. And then in this part that we are H1 divided by omega 0, that's the non-periodic part. Here is the periodic part in omega 0. H1 over omega 0 corresponds to the non-periodic part. So the geometric nilpotent endomorphism, so we're going to define a geometric nilpotent endomorphism through the following form. You take alpha, so you take any path, closed path in the fiber, you intersect it with these CL, which are these circles around the axons. So you see how many times the curve alpha is passing through the axon. And then you weight this with this twisting factor of the then twist, which is coming from the geometric monodromy. And so we obtain a map which goes from one cycles into vanishing cycles, because it's in the module generated by the CL, by this CL. And so and then if you take a homology class that stays in one of these neurons, then this will be 0. So this NG is 0 on the periodic part, and so it gives a map from H1 divided by omega C by H1 divided by omega 0 into omega minus 1. So this is the geometric version of the algebraic result that I mentioned. This is the composition into a periodic and unipotent part. Here, the N comes from this geometric description. And then we construct a non-degenerate bilinear form, similar as before. You take alpha and beta, and then you apply the NG. I'm sorry, this is the NG with beta, and then it looks like this. So the geometrically defined bilinear form, you intersect alpha. So you take alpha and beta 2 cycles. You intersect alpha with CL, beta with CL. You multiply them. You put a weight which corresponds to this then twist, and then you divide by n, which was this number, which was measured the periodicity of the function on the neurons. And this bilinear form is positive definite directly from the formula, because here we will take alpha with alpha. This will tell us how many times did alpha pass through the axon CL. You square it, and then you multiply by ML, and you divide by 1/n. So these ML are all positive, and this comes from complex analysis, in the sense that all the functions, all the twists that we do, all the dent twists are orientation preserving. So these ML are all positive, and so this is what makes this geometrically defined bilinear form a positive definite form. Now, the homology to a power to the n will be the identity, and then it will have this part over here. So here we are putting a basis where we begin with omega minus 1, then omega 0, and then the rest of H1. This, we're dividing into blocks the homology. And then the nilpotent matrix looks like this, and the part which is non-zero is like this. So, so the geometric flag is preserved by the monodromy. You have the vanishing containing the periodic in the 1 cycles, and you have this geometrically defined nilpotent map. It is nilpotent because if you take CL, it never crosses any other CL. So the bilinear form, the coproduct is 0 restricted to these CLs because they don't intersect. And so, so the non-degenerate bilinear form that we obtain is positive definite, and it codifies this Jordan block structure of the map H star to the n. So the theorem we have is the following: all this group of people that I mentioned in the beginning, given a germ of a holomorphic function with an isolated singularity, then the algebraically defined weight filtration and the geometrically defined weight filtration coincide. The geometric and the algebraic bilinear forms coincide. The graph gamma tilde with the positive definite bilinear form in H1 of this gamma tilde is what is called a polarized tropical curve. And so this makes a bridge between this resolution of singularities and Hodge theory with a more modern part of algebraic geometry that is called this tropical geometry. And if we take, as I mentioned, this basis of H1 ordering according to this weight filtration, then the matrix of intersection product in H1 has the following form. So that's why to make this the composition, it makes a special description of the bilinear form. And so here we have some zeros, and in here we have this, this is Q0 is the coproduct on the neurons. Q1 is this bilinear form that I mentioned, which was positive definite, and this is because it's an anti-symmetric bilinear form coproduct. And so, ¿cómo vamos de tiempo, Eduardo?
Time.
Okay, so now
you're still having 10 minutes to finish your conference, so don't worry.
Okay, so now I will describe 3 examples. Take the following function, x6 plus y7 times x7 times plus y6. It defines a singular point of a plane curve with Milnor number 131. That's the rank of H1. And its characteristic polynomial is this one. So this you can see what are the eigenvalues of the monodromy map. And over here, this delta 2 is which are the eigenvalues, but just restricted to the Jordan blocks of size 2. And that's this. So here you can see that you have t to the 6 minus 1 over t minus 1. So these are the 6 roots of unity except 1. So these are five cycles. Now in here you can see 1. So you go into 1 and you return with the other. So this is, you have 1, 2, 3, 4, 5, 6. So there in this case, so this part over here I didn't draw because they contract. They don't give anything to the topology. Also, this other one, they don't give anything to the topology. The only ones that give part to the topology is this part over here. And in here, so we have six loops which connect. So this means that we have 2 neurons and there are 6 axons. And so if you go through one axon and you return through another one, then you have a one non-trivial homology class. Of this, we have 5 homology classes. And so this is described over here. And then you can compute this matrix of bilinear form, this bilinear form that I described, which was positive definite. And so you can explicitly compute in this example this. Now, if you take a more complicated term, so take y squared plus x cubed to the square. So you take this one. What it has is that it has 2 Puiseux pairs. So it has 2 irreducible components, and each one has 2 Puiseux pairs. So in this case, the eigenvalues of the monodromy map is this one, and over here you have this the monodromy, the eigenvalues of the Jordan blocks of size 2 are this one. So here you can see that you have so these are I minus I and minus 1 here. So you have 3 loops. Now the graph of the resolution is this one. The graph of this Nielsenthurston graph associated is this one. And in here you can see the generators of the homology. So here is one, here is another one, and then and here is the third one. And in this one, if one may compute what are the intersections, this bilinear form that I'm describing. So this bilinear form is containing the information about the twist the then twist. So this is like a bilinear form which concentrates information on the then twists, and so is one can compute it, and it looks like this. And we can go to a more sophisticated example, like this one has 4 irreducible factors, and this is the monodromy, the characteristic polynomial of the algebraic monodromy, and this is the characteristic polynomial of on the factors which have Jordan blocks of size 2 are these ones. So this may be computed algebraically, and so in this case the graph, the resolution graph looks like this. Here you can see the 4 irreducible components. This one over here, it may be contracted over here, and so here you have this in here. So we have 2 loops. So there are 2, 1 and 2, and then I don't see at the moment why it was 3 over here, but anyway. So here we have 2 loops, and so you can do even more complicated examples, you know. So here we have this. We are comparing the dual graph of this function on the left and then on the right. So we have 2 different functions, and this bilinear form serves to differentiate these 2 resolution graphs because they don't have bilinear forms which are equivalent. And so this research which I mentioned constitutes only the topological part of the research that in progress. And so what we're having here is this bilinear form obtained by applying this n. And now there is another more algebraically defined, analytically defined, which is this Grothendieck duality, which is a symmetric bilinear form defined on the ring of germs of holomorphic functions modulo the partial derivatives. So this is what's called the Milnor algebra. We have a non-degenerate bilinear form, and the bilinear form is done like this. You take 2 functions, you multiply the functions, you multiply by DC1 exterior DC2 to make a 2 form, you divide by the partial derivatives, and then you take the residue on the 2 homology class formed by absolute values of the partial derivatives equal to epsilon. So this is Grothendieck duality, and so we are our aim in this research is to understand what is the geometric meaning of the bilinear form obtained by applying an extra f on this factor. So in here we apply the n, and in here we apply the f. So this has a more analytic ingredients than the one I explained, which was only a topological part. So thank you for your attention, y felicidades, Enrique. Thank you very much.
Thank you, Professor. It was a very interesting talk. Does anybody have any question? No questions at all? Okay, because I have one.
Yes, I have one.
Sorry, Professor Porter. Please, Professor Porter.
Yes, Professor.
Oh, it seems to be that
You hear me all right?
Your microphone is too noisy.
It's having some problem. Yes, I'm having some trouble. Okay, well, thank you very much.
Okay, well.
If you can't hear me.
Yes, you sounds better now.
Would you write a question in the chat?
Okay, well, while Professor Mike is writing down the question, I have one. You know that the problem that you are analyzing is very related to the complement of singularities. That is, you have the singular hypersurface, and if you want to analyze the complement of this hypersurface, you have the problem of how to represent when the cycles in the complement of the hypersurface are represented by Lagrangian surfaces. Have you considered this problem? The representation of cycles by special curves?
The representation of the one homology classes.
Yeah.
No, I haven't. So this is the complement of the hypersurface of the singularity, and then
Exactly.
you want so that has some H2, no?
Yes, indeed.
So
Yeah,
some H2.
The interesting point is in situ because the representations cannot be that simple. But in particular, you cannot have a representation by cycles which are Lagrangian everywhere. But what happens is you suppose that the representant is Lagrangian everywhere, but a finite number of points.
Okay, I see. Yeah, I haven't I haven't done this. No. So to answer Mike Porter's question, so he's asking why is the dent twist always a positive number and not a negative number? So the fact is that these dent twists are always produced at the intersection of two of the exceptional divisors, one with multiplicity M1 and the other with multiplicity M2. So one has to look only at the function X M1 times Y M2. And then one assumes that M1 and M2 are relatively prime, because if not, then there's just different components. So one has to understand the fibers of the function xm1 times ym2, and then one computes explicitly in this example, and one sees that the dent twist, after you iterate m1 times, it gives you m2. So in that sense, the amount of dent twist is given by the multiplicities of the exceptional divisors on the resolution, and these are both positive numbers, and so it's a simple calculation on this explicit. So the fact that the resolution of singularities, it reduces the function f into monomials, into monomials. It gives you that it's always positive. So the positive definiteness of the bilinear form comes from this this now on the analytic case, this positive definite becomes these Riemann-Hodge bilinear relations. So the analytic case, so we have a geometric proof of these Riemann-Hodge bilinear relations for this case. Now there was another question by Mike that whether we do these computations by hand. No, we do these computations for the more complicated examples that I explained. We do them on the computer. So it's so there is this theory. Let's see. Okay. So we do them by the examples by computer algebra.
So any other question? Anyone? Well, thank you, Professor Gómez-Mont. It was a very interesting conference, and we are having a break of 7 minutes. So we stop recording.